Good morning, students. So in the previous classes, we discussed the one-dimensional problem on infinite quantum well and finite quantum well, and we consider the wave. We calculated the wave function. We considered the boundary conditions. We applied the Schrödinger equation, and we could find out the expression for energy. And in the next class also, we discussed the finite quantum well, and we could find out the wave function using Schrödinger equation. We applied boundary conditions, and we calculated the energy eigenvalue. And in fact, the result of the finite quantum well exactly matches with the infinite quantum well. So this is what we discussed. And this is also about a one-dimensional problem, but this is much more important than those two problems. So this is a potential barrier, square potential barrier. This time we are going to get the transmission coefficient. We are not going to get the wave function as such we calculated for the two problems and energy eigenvalue, but we are going to get the transmission coefficient, the probability of transmission, how far the wave function can penetrate into the barrier. This is a peculiar quantity in quantum mechanics. It's a weird one. Of course, in classical physics, if I have a barrier, if I want to throw a ball and I have to give more energy than the potential energy of the barrier, only then it can cross. The ball can go from left to right. Whereas in quantum mechanics, it is not the case. There occurs a tunneling property. The waves can penetrate into the barrier. Even though the kinetic energy is less than that of potential energy, there is a possibility of wave function that can penetrate into the barrier, and it can go across the barrier. So this is called quantum tunneling. So out of this quantum tunneling, many experimental results that we can obtain. For example, the famous one is STM, scanning tunneling microscopes. So it's a kind of microscope which was invented by Binning from Germany 1971, for which he got Nobel Prize 1976. Binning. We can analyze the surface of any nanoparticles. The manipulation of atoms can be done by means of STM. So in scanning tunneling microscope, there will be a small tip. It will be in the order of micron. Small tip will be there, and you are going to analyze the nanofilm. Just keep the tip nearby the film. You should not touch the film. So you are going to keep the tip nearby the film, and you are going to give the voltage. This voltage for both the things. This voltage variation that will cause the current that will go from the tip to the surface on the film, and we can have some fine image of the film. So if it is a nanometer, and easily one can analyze the image. So STM is very, very famous nowadays. And alpha decay. The theory which says that the parent nuclei that can convert into some small children nuclei, some new nuclei. So that's called alpha decay. That comes under the process of tunneling. Tunnel diodes exist. So there are a lot of things that can be obtained by means of this quantum tunneling. Quantum tunneling is a very, very important property in quantum mechanics, which we will not study in classical. So classical will never study. There is no quantum tunneling exists. Whereas in quantum mechanics, quantum tunneling exists. Penetration of the wave functions. So we are going to see in detail about the transmission coefficient. How far it can transmit. The wave function can transmit through the barrier. How long it can transmit. What are the factors it can depend on? Of course, it depends on the well size. If barrier is very thin, easily it can penetrate. Barrier is very thick, it's very hard to penetrate. So we know. So it depends on the well size, and of course it depends on V0 also. Okay. So today we are going to discuss in detail about the square potential barrier. So finite potential barrier and tunneling effect, we are going to find the transmission coefficient. We are not going to find out the wave function or eigenenergy values, but more than that, very important thing is transmission coefficient, reflection coefficient, but above all, transmission coefficient is very important. Consider a case of a potential barrier. So this is a potential barrier. It extends from 0 to L, 0 to L of the region. The height is your V0, which is constant in the region, and potential is 0 elsewhere. So potential is 0 on both sides. Inside it is constant. So it can be 200 MeV or it can be 500 MeV, 2 electron volt. So something like that. So we have the potential. This potential height is constant here inside the potential barrier, and it is equal to 0 on either sides. So it's given. A stream of particles which is incident from the left to the barrier. So stream of particles which are coming from left to right. Now there are two cases where the energy of the stream of particles is greater than your potential barrier and less than your potential barrier. So there are two cases which we are going to discuss. Okay, so there are three regions: first region, second region, and third region. And of course the potential is given exactly like this: V0, which lies inside the barrier. It lies, x lies between 0 and L. We have V0. On either side, this is 0. So potential on either side it is 0, and here the potential height is V0. Okay, so this is all about the diagram of finite square potential barrier. Okay, we are going to consider two cases. As I said, corresponds to a particle larger and smaller, and of course we know that classically it can go from, if energy is greater than V0, it can go from left to right. We discussed already. Okay, it can go from, there will be no transmission, and it can go from left to right. Whereas in quantum mechanically, some particles will, there is a chance of penetrating into the barrier. Okay, some particles can be reflected. Okay, so that we are going to discuss. So the particles, this is for the classical region and this is for the quantum mechanical region. In quantum mechanical region, some particles will get reflected back. It can come back. Okay, so this is what it is given. On the other hand, in case of E less than V0, classically the particles will always be reflected as the kinetic energy of the particle is negative in the barrier, and hence the motion is forbidden classically. Okay. However, in quantum mechanics, the particles have some probability of penetration into the barrier and therefore appear in the region x greater than L, and this probability increases with the condition V0 minus E becoming very, very small. As I said, the barrier thickness, it depends on the thickness of the barrier. Thus the particles have some probability of transmission through the barrier, and this effect is known as tunneling effect. Okay, which we are going to discuss, the transmission coefficient. This phenomena is nothing but tunneling effect. Okay, so as we said, there are three regions. First region, the first one. Second region is the potential barrier, and third region will be at the right side. So when this condition E is greater than V0, the Schrodinger equation for the first region is given by d squared psi by dx square. This is for the one dimension. This is for the one dimension. D squared psi 1 by dx square plus 2m by h bar square E psi 1 equal to 0. As I said, first region and third region V equals 0. So here there is no V here. V equals 0. So d squared psi 1 by dx square plus 2m by h bar square E psi 1 equal to 0. And we can write 2m E by h bar square, which is nothing but k1 square. We discussed earlier in the class itself. So description is given. K equals 2 pi by lambda. Use de Broglie's concept. So you have lambda equal to h by p. So 2 pi p by h. E equals p squared by 2m. So your p will be root of 2em. So 2em divided by your h bar. Okay, h divided by 2 pi will be your h bar. So this will give you k squared equal to 2m e by h bar squared. So we can replace this term into k1 squared. So this is in the region first. Okay, the solution of this equation. So solution of this expression is given by psi 1 equals a e power I k1x plus b e power minus I k1x. So this is for the reflection and this is for the incident. So we have the graph exactly like this. So this is for the incident. incident and reflection. So we have both the wave functions here. One is e power ikx, another one is e power minus ikx. And this coefficient is very important. Okay, so incident, so this coefficient is meant for incident. This coefficient is meant for reflection. Okay, these two coefficients are very important. And region 2, we have d squared psi 2 by dx squared plus 2m by h bar squared e minus b naught. We have put the condition e is greater than b naught, correct? So it must be e minus b naught. In the last class, b naught minus e. Okay, so you should not get confused. So e minus b naught psi 2. So v naught exists. Okay, v naught is constant in the potential barrier. And of course, we can replace this by k2 square. Okay, so the general solution is given by k2. So this is not k1, this is k2. So psi 2 equals c e power I k2x plus d e power minus k2x. Okay, and of course, inside the barrier, some waves will get reflected. So this is for the reflection. Okay, at the boundary inside, some waves. See, for example, here you have incident. Okay, incident wave. As well, you have reflected waves. Okay, now some waves, as I said, they will penetrate, and it will penetrate, and we have penetration. This is for C for the penetration. Okay, it will penetrate, and some waves will get reflected. So these waves will get reflected. Now again, due to tunneling effect, it can cross the barrier and will go that side, and there is no reflection here. Okay, there is no reflection here. There is no e power I term here. So we have reflection term here. That's why e power I term. Here we have reflection term because of this one. There is no reflection here. It will go from left to right that side. So there is no minus term here. Okay, in the third region. Now in third region, d squared psi 3 by dx squared plus 2me by h bar squared, psi 3 equal to 0, and the same thing that we have to write. So this can be replaced by k1 squared, and your psi 3 will be this one, and this is absent. You will get only this term alone. Okay, so there is no reflection in the third region. So that's why the psi 3 is given by f e power I k1x. Is it okay? So just look at the picture here. We have incident wave function, and some waves will be reflected, of course we know, and due to the tunneling, it has to cross the potential barrier, and it will come back, so reflection, and it will go that side. Okay, and these are the corresponding wave functions. So we have wave functions. Psi 1 is here in the first region, psi 2 is here in the second region, and psi 3 is here in the third region. So we have linear combination of two wave functions on first region and second region, and there is a single wave function because there is no reflection in the third region. So is it okay? Very simple. Now our aim is to find out the transmission coefficient. So this is what we are going to learn today. Okay, to learn transmission coefficient, what we are going to do, we are going to, of course, we are going to use Schrodinger equation. We are going to use boundary conditions. So we are going to use Schrodinger equation. We are going to apply boundary conditions. Okay, of course it is there. Okay, J incident is probability density of incident flux. J stands for flux, incident flux, which is equal to h bar k1 divided by m mod a square. As I said, this a is very important. Okay, what is a? What is a? Of course, normalization constant, and here it is. This is about incident. Okay, this is connected with the incident wave. So mod a square. Okay, J reflection. So probability density of J reflection flux will be in the first region will be given by this. So of course this is plus quantity, this is minus quantity. Okay. Now J transmission is given by this. So J transmission. Okay. So now your J transmission we are going to find out. This is transmission probability we are going to find out, which is nothing but F, that is mod F square divided by mod A square. This is the ratio of F and A will give you transmission coefficient. Okay, square of transmission coefficient. And we are going to take the root that will give you T equals F by A. So if you know F, the coefficient of the last region, okay, if you know F, that is transmitted flux, okay. If you know the coefficient of transmission flux, if you know the coefficient of incident, the constant, we are going to have the ratio that will give you transmission probability or transmission amplitude. So this is what we are going to discuss. So we are going to use Schrodinger equation, first point, and we are going to apply boundary conditions. We are going to get the value of f, we are going to get the value for a, and divide these two, that will give you transmission coefficient. So this is the idea behind this potential barrier. Okay. So now we are going to get a, b, c, d and f. Those are all constants. Why I have not written e here? Because e is always meant for energy. So that's why people will skip the term e, the letter e. So a, b, c, d and f. So we are going to use the Schrodinger wave equation. As I said, we are going to apply the boundary conditions. What is the boundary condition? Boundary condition, the first region, the wave function exactly at the boundary at x equal to 0 on both sides. Okay, that is psi 1 which is equal to psi 2 at x equal to 0. So psi 1 is here, psi 2 is here. You substitute at x equal to 0. So e power ikx, so e power 0. So you will get a plus b e power minus ik1 is there. I can write this as 1 by e power ik1x. So 1 by e power 0, 1 by 1, which is answer is 1. So if you substitute x equal to 0 here, you will get a plus b. So a plus b. Okay. And psi 2 which is equal to x equal to 0. Psi 2 at x equal to 0 will be c plus d. You just equate these two, that will give you a plus b plus c plus d, which is the equation 2.64. Any doubt? So we are going to apply the first boundary condition and we have obtained this. Now the second boundary condition, we are going to differentiate. Differentiate with respect to x at x equal to 0 and equate the next region. Okay, the wave function, the next region, derivative of the next region. So when you are going to differentiate, that will give you d psi 1 by dx will be ik1 e power ik1. So ik1 a ik1 e power ik1x. Similarly, minus b ik1 e power minus ik1x. And differentiate this, that will give you this expression, correct? Ci k2 e power ik2x minus di k2 e power minus ik2. So now at x equal to 0. So you have to substitute at x equal to 0. At x equal to 0, that will give you ai k1. So ai k1. So minus bi k1, which is equal to ci k2 minus di k2. Okay. You pull k1 out on both sides. Okay. Here k1 out on both sides. Here k2 on this side. Okay. I get cancelled. So you will get k1 a within bracket a minus b, which is equal to k2 within the bracket c minus d. So a minus b equals k2 by k1 c minus d. So our aim is to find out a, first a. Okay, our aim is to find out a. Then our aim is to find out j. J by a, that will give you t, transmission coefficient. So this is our idea. Okay. Now a minus b. Okay. So let it be. Now we'll go for the next boundary condition. Next boundary conditions at that region. Okay. Second region and third region. So psi 2 at x equal to L, which is equal to psi 3 at x equal to L. Okay. See, we have the boundary condition. Two boundaries are here. Okay. So this wave function is equal to this wave function at this boundary. This wave function is exactly equal to this wave function at this boundary and derivative also. And we have considered and we have obtained a minus b, that relation. And we are going to use this one now. Okay. So psi 2 at x equal to L, which is equal to psi 3 at x equal to L. Psi 2 is given by Ce to the power ik2x plus de to the power minus i2x. So psi 3 is given by this. So there is no reflection coefficient there, psi 3. Okay. Now you are going to equate these two at x equal to L. So this gives you Ce to the power ik2L plus de to the power minus i2L, which is equal to fe to the power ik1L. Okay. Is it okay? Now differentiate this with respect to x. So differentiating, that will give you, differentiating this, that will give you Cik2 e power ik2x at x equal to L minus dik2 e power minus ik2x at x equal to L. So differentiate, that will give you f ik1 e power ik1x at x equal to L. So you know, substitute x for L. Okay, you are going to substitute L for x. So that will give you C I get cancelled, of course. So you will have C e to the power I k2L. You just bring k2 to that side. K2 just take common. and bring that k2 to the right hand side. So that will give you f k1 by k2. You substitute x for x, substitute for L. So C e to the power I k to L minus d e to the power I k to L, which is equal to f k1 by k2 e power I k1 L. Is it okay? Now, the previous thing, we have a plus b equals c plus d, correct? The first condition. And the next one will be a minus b equals k2 by k1 c minus d. You just add these two. That will give you 2a, bb will cancel, c plus d plus k2 by k1 c minus d, correct? So c plus d plus k2 by k1 c, I have separated, so minus k2 by k1 d. Just take c common out. So c 1 plus k2 by k1 plus d common out, that will give you d1 minus k2 by k1. Okay. So divide by 2. Okay, divide by 2 and take divide by 2, that will give you c by 2 1 plus k2 by k1 plus d by 2 1 minus k2 by k1. Similarly, you add these two. Okay, for another boundary conditions. Okay, you just add these two. So if you are going to add these two, that will give you, this will cancel. You have 2c e power I k2L, which is equal to, add these two, that will give you f e power I k1L plus f k1 by k2 e power I k1. You pull f common out. So that will give you f in bracket 1 plus k1 by k2 e power I k1L. Okay. As usual, you just divide by 2. One. Second one is, you bring this term to right hand side. So we will get the value for expression for C. So C equals f by 2 1 plus k1 by k2 e power I k1L. This term goes that side. So e power minus I k2L. So is it okay? 2.75 expression. Very simple one. Similarly, just to subtract these two. So last time we added, we got the value for C. Now just to subtract, you get the value for D. That's all. So subtract these two, that will give you. This one will get cancelled. You have 2D, correct? 2D you will get. Divide by 2, that will give you f by 2. So now this term will be right hand side term. F by 2, 1 minus k1 by k2 e power. You have to bring that term, e power minus I k2L to that side. So that will give you e power I k1 plus k2 in bracket L, as we have done in the last expression. The same method. That is, you just subtract, divide by 2 and bringing this term e power minus k2L to the right hand side, you will get this expression. Okay. So now we have found out the value for expression for C and D. You substitute in the expression for A. So we have obtained now the values for C and D, correct? So we got the expression for C, we got the expression for D. You substitute in this expression, you will get the value for A without the constants. You will get only A alone. So there will be no C, there will be no B, there will be no D at all. Okay, so that's the idea. Now already we have found out our C value, C expression. We have found out the D expression. You substitute in this expression, you will have A equals C equals what is f by 2, this one. Already 1 2 exists. One more 2 it will come. Okay, so you will get f by 4 1 plus k1 by k2. This expression is 1 plus k2 by k1. Okay, your e power I k1 minus k2 here. Is it okay? So plus your D, expression for D is here. So you will have f by 2, already D by 2 is there. So f by 4, 1 minus k1 by k2. This expression 1 minus k2 by k1, and this expression e power I k1 plus k2 there. So is it clear? See the idea now. You have A on left hand side. You have F on the right hand side. F by A, that will give you transmission coefficient. So that's the idea. So F by A. Okay. So now we will simplify some terms out. Okay. So e power I k1, I pull e power I k1 L out because e power I k1 is common. I can't do this one because that is e power plus I k2. This is minus k2. So I can only pull e power I k1 out. Okay. So remaining term 1 plus k2 by k1 1 plus k1 by k2 e power minus k2l plus 1 minus k2 by k1, 1 minus k1 by k2 e power I k2. Now take the LCM. Okay, we just take the LCM. So we have this term. I have written the same term here, 2.78, same expression here. Okay. Now e power ikl I can bring it to this side. Okay, and a I can bring it to this side, and 4 also I can bring it to this side. So that will give me 4 e power ik1l, which is equal to f by a. F by a is nothing but my transmission commutator and the remaining term. So we have calculated now expression for f by a. So f by a equals 4 e power minus ik1l l divided by this term. We will simplify. Okay, we will try to simplify. So we have 1 plus k2 by k1. Okay, just take the LCM. So that will give you k1. So here you have k1 plus k2 divided by k1. Here you have k1 plus k2 divided by k2. So k1 plus k2, k1 plus k2, k1 multiplied by k2. This term let it be like this. Similarly, just take the LCM. K1 minus k2. Okay, you have k1 here. K2 minus k1 divided by k1, k2. Okay, so this is, we can square this term, but we can't square this term. This is k1 minus k2 multiplied by k2 minus k1. No other way. We'll have to multiply these two terms. So we can square this term out. Okay. So when you square this term in the denominator, k1 plus k2 whole square divided by k1 k2 e power I k2l. Okay. This term I have written as it is, k1 minus k2, k2 minus k1. So again take the LCM k1 k2. Here also we have k1 k2. I can bring it to the numerator. So this will become 4 k1 k2 e power I k1l divided by a plus b whole square formula. So you have k1 square plus k2 square plus 2 k1 k2 e power I k2l. Okay, the remaining term I have written the same thing, k1 minus k2 into k2 minus k1. Okay, I have written the same thing here, and this term I have multiplied k1 k2 k1 k1 and k2 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 k1. So you have k1 and k1, that will give you k1 square. Okay, and k2 k2, that will give you k2 square. The remaining term will be k1 k2 and k2 k1. So you will have k1 k2 e power I k2l, and this term with the 2 minus signs. Okay. Now this term I have written k1 square plus k2 square e power minus k2 out. This term alone I have separated. Okay. So k1 k2 and k1 k2 I have added, I have written here. Okay. And these two terms I have written separately. Is it okay? See, these first two terms I have written with the e power I minus ik2l. Second term I have written exactly as is. I have added these two terms, and I have written combined. I have written k1 square plus k2 square e power I k2l. Okay. Now these two terms I can combine. So numerator as it is like this. I have written same expression 2.85. So I can combine now k1 square plus k2 square. Here also you have k1 square plus k2 square. You have e minus sign is there. So I have written with a minus I. Okay. So e power I k2l. Here e power minus I k2l. And the remaining term 2k1 k2. Remaining term you can combine, that will give you e power minus I k2l. So this will be e power plus e power I k2l. Okay. Is it okay? 2.86. Multiply and divide by 2. Here also multiply and divide by 2. Inside alone. So that will give you here 2 is there. This 4 and 2, that will strike it off, and you will have 2. Okay. So here you have 2 divided by 2, and here you have divided by 2. So e power I k2l minus e power I k2l divided by 2, e power minus I k2l plus e power I k2l divided by 2. Okay. So what is the necessary? We have multiplied and divided by all because of this. Sin k2l equals e power I k2l minus e power minus I 2k. Similarly, cos k2l is given by e power x plus e power minus x divided by 2. Okay. So this term can be written as But you just look at it. This is e power plus ik to L minus e power minus I to L. But here it is given as e power minus I to L minus e power of ik to L. Okay, plus ik to L. Okay, minus e power of ik to L. Okay, so for that what we can do, just minus I. So you just bring this I and minus sign, that will give you minus I. Minus I k1 square plus k2 square. This can be replaced by sin k to L. And of course this is very simplified one. So 2k1 k2 cos k to k. Is it okay? So we have found out now f by a. The complete expression for f by a. The transmission, the square of the transmission coefficient, as we discussed earlier, which is nothing but f by a multiplied by its complex conjugate. Modulus of f square divided by modulus of a square. So we will have to take the complex conjugate, multiply, take the square root, that will give you your t. So that is the answer. So now we are going to take the